So as said, we will be doing magnetism today. So as per NCRT, first he has given moving charges in magnetic fields. So basically I thought of presenting the basic concepts of magnetism and then proceed to moving charges in magnetism. Because what all units, terms, what we adapt in that moving charges in magnetism uh, will be learned in pure magnetism. Of course, the modern science unified theories removed the bar between the electricity and magnetism. They are unified theories, electromagnetism, but it is customary for us to know the basics of magnetism before we go to the electromagnetism. And I'll be doing it in comparison with electrostatics so that those things also will be analogy between whatever analogy is there between electrostatics and magnetostatics can be understood. Things can be done little easier. Plus, it will be a kind of revision for you. That is what I planned. So, I'll be doing in comparison with electrostatics. Okay.
Yes, sir.
So, in NCRT textbooks, it is 12th, volume 1, chapter 5. So this is what we have already learned in electrostatics. And this is what we have in magnetism. So to begin with, the intrinsic property of the matter which is responsible for the electrical interactions is the electric charge, which is measured in coulombs with the dimensional formula Ti. The similar term in magnetism is pole strength. Pole, sorry. So, just as we have positive and negative charges, magnetic pole. In magnetism, we have the north and south poles. So the region of the magnet where the magnetism is enriched more, that is called as pole. Normally, the two ends of the magnet, in case of a current carrying coil, the two faces of the coil will be considered as the poles. And the ability of the pole to influence other magnetic pole is measured in terms of pole strength. So the measure of magnetic pole to influence other magnetic poles, that is called as pole strength, and we have units of ampere meter with the dimensional formula Li. This is about the electric charge. Next we have the electric dipole. So it is a set of equal and unlike charges separated by a finite distance, that is called as electric pole. In the similar manner, the set of equal and unlike poles separated by a finite distance, we call it as magnetic dipole. And the shortest distance between the two charges of the dipole is 2L. Here also it's called magnetic length. Magnetic dipole length. There it is electric dipole length, here it is magnetic dipole length. Then the next one is, third one, electric charges, I mean the existing positive and negative charges are separable, whereas magnetic poles it is always dipole only. Means these north and south poles in a magnet exist together. So you have electrons and electrons orbiting electrons around the nucleus, while the positively charged protons will be inside the nucleus. So they are separable. If you remove electron, remaining will be the positive ion of the atom. Whereas even if you go up to the atomic dimensions, every atom will behave like a dipole. So every atom will behave like a dipole. Hence, magnetic monopole does not exist. That is the important point here. Then, the electric field. If I have a positive charge, then there will be a region of its influence. Either that is the region in which it either repels a positive charge or attracts a negative charge. That is called as electric field. So practically magnetic monopole will not exist, but for all theoretical considerations, we assume that an isolated magnetic pole will exist. Theoretical considerations, I'm very carefully using the words. So here is the magnetic pole, say North Pole. The region around this magnetic pole where its influence will exist. That is, for example, a unit North Pole is there, it will be repelled. A unit South Pole is there, it is attracted. So that region of influence is called as the electric field. Then we also define electric field lines. So the imaginary line drawn along which a unit positive charge moves, that is called as electric field line. So there, of course, we said field lines were drawn for isolated charges. We have drawn even for dipoles and even for pair of like charges too. In the same manner, here is a magnet, here is a north pole, here is a south pole. If you place a unit north pole near this north pole of the magnet, then it follows a well-defined path like this. So, the lines of force will be moving from north to south pole, and this is called the path followed by a unit north pole when placed in the magnetic field. That is called as magnetic field line. Even we have studied the properties. The field lines will be diverging from positive charge. They converge near the negative charge. Next, isolate electric field lines can be drawn for isolated charges as well as dipoles, as well as pair of like charges. Next, they are discontinuous because dipoles will not exist there always. More number of electric field lines in the given space near the electric charges than at some distant point indicates that the field is more stronger near the electric charge than at the distant point, and the lines of force will always appear to be under tension. So they will be linearly converging and laterally diverging, and electric field lines will never intersect with each other. So these are all the properties what we have studied. In the similar manner, you can list out the properties for magnetic field lines. The magnetic field is, because we always talk about unit positive charge in electricity and a unit north pole in magnetism. Hence, we always talk about the unit north pole and start from north pole of the magnet. Therefore, the magnetic field lines will be diverging from the north pole and they converge near the south pole outside the magnet. Next, the magnetic field lines are closed curves and they'll be moving from south to north pole inside the magnet. This is another difference between the electrostatics and magnetostatics. I repeat, the electric field lines will be diverging from north pole and converging near the south pole. Next, inside the magnet, they will be moving from south to north pole. That is, the field lines, the magnetic field lines are closed curves. Next, more number of magnetic field lines in a given region of space near the poles than a distant point indicates that the magnetic field is more stronger near the poles. Next point is the tangent drawn to the magnetic field line at any point will be giving you the direction of electric field at that point. Next, the magnetic field lines appear to contract linearly and diverge laterally. And magnetic field lines will never intersect with each other. The reason already I told you there in electricity, if you assume that the magnetic field lines are intersecting, the field at one instant should have two different directions, which is absurd. So this is about the magnetic field lines and properties. Have you copied?
Yes.
Yes, sir.
Okay. Then sixth one, permittivity, epsilon. So the extent up to which the influence of an electric charge can pervade through the given medium is termed as permittivity there. So this is what we have shown. If you have a conducting material like copper, the field lines will prefer to go through the vacuum than through the copper. Whereas if you have a glass or bakelite, an insulating material, the lines of force will be going through them. So field line is the measure of influence of an electric charge. So the measure of extent up to which the influence of an electric charge can pervade through the given medium is called as permittivity. Coming to this in magnetism, of course, in vacuum, in vacuum, permittivity is given by epsilon 0. This is of course 1 by 36 pi into 10 to the power of minus 9 farad meter inverse, or 8.85 into 10 to the power of minus 12 farad meter inverse. And even we defined the relative permittivity or the dielectric constant or specific inductive capacity as the ratio of absolute permittivity of the medium to permittivity of vacuum. And for vacuum, epsilon r value is 1. Coming to this magnetism, we have a similar term, permeability, represented by mu. So here I have same copper. The field lines prefer to go through the vacuum, and I have aluminum. Few out of large number of field lines prefer to go through aluminum. Here is soft iron. All the field lines manage to go through this soft iron. So based on this ability, we classify the materials into 3 types in magnetism. This is diamagnetic, paramagnetic, and ferromagnetic. So the extent of influence of the measure of extent of influence of a magnetic pole is called as permeability, or the measure of ability of a medium to allow the magnetic field lines to pass through it. That is called as permeability. So for vacuum, the value is mu0 is equal to 4 pi into 10 to the power of minus 7 Henry meter inverse. And just like in electrostatics, here we define relative permeability. Represented by mu r, which is the ratio of absolute permeability of a medium to the permeability of vacuum. So here, for diamagnetic substances, the relative permeability is less than 1. For paramagnetic substances, the relative permeability is greater than 1. For ferromagnetic substance, it is very high. Will be in the order of 100. So this is about the permeability.
Sir, could you once repeat permeability definition, sir?
Yeah, the measure of extent up to which the influence of a magnetic pole can pervade through the given medium. Pervade means penetrate, pass through. Or it is the measure of ability of a medium to allow the magnetic field lines to pass through. Measure of ability of a medium to allow the magnetic field lines to pass through. Okay, na?
Yes, sir.
Yeah, this you should have the idea. So for diamagnetic substances, mu r is less than 1. For paramagnetic substances, mu r is greater than 1. And for ferromagnetic substances, very high. So the range will be in the hundreds. Next. 7th one is electric flux. So here is the surface. These are all the electric field lines. These are the electric field lines from the given charge. So out of large number of electric field lines crossing the given surface, few of them will be crossing the surface normally. So the total number of electric field lines crossing the given surface normally is called as the electric flux, and it is given by the charge enclosed by epsilon 0. So this is what we have, charge enclosed by epsilon 0. Similarly, coming to the magnetic flux, here is a given surface, and these are all the magnetic field lines. Like this. So here also we define, if you want you can note down the definition. The total number of magnetic field lines crossing the given surface normally. The total number of magnetic field lines crossing the given surface normally is the measure of the magnetic flux is the measure of magnetic flux, and it is given by, of course, in vacuum, it is mu 0 times the pole strength. Here the units of electric flux, Newton Coulomb inverse meter square. Whereas here, this is Weber. Capital U, capital W and B, Weber. And pole strength units, I put it as ampere meter. So there is a relation between them. 1 Weber will be equal to mu 0 times the ampere meter. You must remember this. 1 Weber is like 1 meter is equal to 100 centimeters. In the same manner, Weber is the practical unit for pole strength, you can say. So 1 Weber is mu 0 times the ampere meter.
Sir, can you please repeat the definition of
Magnetic,
flux?
the total number of magnetic field lines, crossing the given surface normally. The total number of magnetic field lines crossing the given surface normally is called the magnetic flux. Finished that?
Yes.
Okay. Yeah, Ramakrishna board was good, right? My compliments to you
Thank you, sir.
for the good suggestion. Yeah, I know only using the things, but I don't know the details of all the software and all. Good. So you're interested in computer engineering,
Yes, sir.
Good. So next one is electric flux density. There is ease in using the board, writing and all, everything is easy. Electric flux density. We called it as, of course, the electric field strength or electric field intensity. So this is given by the electric flux per unit area. So if the given surface is spherical, here we introduce Gaussian surface and all. In say magnetism also it comes like that. So if the given Gaussian surface is spherical, then the surface area will become 4 pi r square. So I will be getting it as 1 by 4 pi epsilon 0 into Q by r square. This was the formula, Newton Coulomb inverse. Coming to this, magnetic flux density. Represented by B bar, or it is also called as magnetic induction vector. So this is given by the magnetic flux linked per unit area. So in the same way, if you assume that the considered Gaussian surface around the pole is a sphere of radius r, then the magnetic flux density will become mu 0 by 4 pi into m by r square. See the difference in formula. And here the unit is Weber meter to the power of -2, that is Tesla. Weber meter to the power of -2, it is also called as Tesla. Here we get an additional point. That is, in CGS units of magnetism, the unit is Gauss. So 1 Tesla is 10 to the power of 4 Gauss. How you get, you may be having a doubt. Yes. This Gauss is nothing but 1 Maxwell per centimeter square. Just as 1 Tesla is 1 Weber by meter square, 1 Gauss is 1 Maxwell per centimeter square. So Maxwell is the CGS unit of flux. And the relation is it's called Maxwell per centimeter square. And 1 Weber is 10 to the power of 8 Maxwells. Next, 1 meter square is 10 to the power of 4 centimeter square. That's how we will get 1 Tesla, that is 1 Weber by 1 meter square, will be equal to 10 to the power of 8 by 10 to the power of 4. That is 10 to the power of 4 Maxwell per centimeter square. That is called as Gauss. Okay.
Yes, sir.
And one more term is there which you will be missing in electrostatics. Only this is applicable to magnetism. That is magnetizing field intensity. Represented by H. Here is a magnetic pole, and this is the imaginary spherical surface. So the field lines from this magnetic pole will be radiating out. They'll be going away from the North Pole. And the radius of this Gaussian surface is R. So the magnetizing field intensity is defined as the pole strength linked per unit area of the Gaussian surface. I repeat, the pole strength linked per unit area of a Gaussian surface is called as the magnetizing field intensity, or simply magnetic field intensity. So its units are ampere meter by meter square. So it is ampere meter inverse. And the dimensional formula is S L inverse I. So here we got B is equal to mu0 by 4 pi into m by r square, and h is m by 4 pi r square. Therefore, we can relate B and h using the formula B is equal to mu0 into h. So in a medium, B is equal to mu h, that is mu r mu 0 h. Of course, for vacuum mu r is 1, you will get B is equal to mu 0 h. But in a medium like with say soft iron or aluminum etc., B becomes equals to mu h. In place of mu, it is mu r mu 0 into h. So this is about the magnetizing field intensity.
Sir, can you please repeat its definition, sir?
Which definition?
Magnetizing field intensity.
Yeah, you can write. The pole strength of the magnetic pole, the pole strength of the magnetic pole per unit area, the pole strength of the magnetic pole per unit area of the Gaussian surface, unit area of the Gaussian surface enclosing the magnetic pole. Enclosing the magnetic pole is called the magnetizing field intensity. Okay.
Yes,
Sir,
sir.
is M here pole strength, sir?
Pole strength, yes. That's why ampere meter by meter square will give you ampere meter inverse.
Yes, sir.
Okay. Understood? Huh?
Yes, sir.
Yes. Then, second part, Coulomb's inverse square law. So there in electrostatics, we wrote these are the 2-point electric charges situated in a medium of permittivity epsilon at a distance r. Then this is the electrostatic repulsive force. So there we said the electrostatic repulsive or attractive force between a pair of charges varies directly as the product of charges, inversely as the square of distance of separation. And we also said this force will always act along the line joining the 2-point charges. So in electrostatic units, we got the proportionality constant as 1 in vacuum. So we got F naught as Q1 Q2 by R square. So in medium, we got F is equal to Q1 Q2 by K into R square, where K is a relative permittivity or dielectric constant. From that only we could say F is equal to F naught by K. And in SI units, we got the proportionality constant. Of course, this is F is equal to P into Q1 Q2 by R square. So in SI units, P value is 1 by 4 pi epsilon in the medium. Therefore, F will become 1 by 4 pi epsilon into Q1 Q2 by R square. And this is written in the next step as 4 pi epsilon or epsilon 0 into Q1 Q2 by R square. And in vacuum, epsilon r is 1. So that's how we got F naught is equal to force in between the poles, electric charges when they are in vacuum is given by 1 by 4 pi epsilon 0 into q1 q2 by r square. And after substituting the value of epsilon 0, we got this finally as 9 into 10 to the power of 9 into q1 q2 by r square. This is all what we got in electrostatics. In a similar manner, I told you practically no magnetic monopole will exist, but it's all for theoretical considerations. So these are the point magnetic poles of pole strengths M1 and M2 situated at A and B in a medium of absolute permittivity epsilon, in a medium of absolute permeability mu, such that theoretically only we are assuming, practically no magnetic monopole will exist. That point you must remember. So this is the repulsive force on first pole exerted by second, and this is the repulsive force exerted by second pole, first pole on second. Repulsive force on second pole exerted by first pole. So we get F varies directly as the product of magnetic pole strengths and inversely as R square. So in vacuum, statement is the magnetic force of attraction or repulsion between point magnetic poles varies directly as the product of pole strengths and inversely as the square of the distance of separation, and this force will always act along the line joining the magnetic poles. So in vacuum here also, that is F is equal to say some P M1 M2 by R square. In vacuum, in CGS units, P will be equal to 1. Therefore, F naught becomes M1 M2 by R square. Next, in medium, F will be just like K there. Here we will get mu R into M1 M2 by R square. In vacuum, mu R is equal to 1. So from this you can say F is equal to mu R into F naught, or mu R is equal to F by F naught. So if you introduce a medium in between the poles, yes, with higher relative permeability greater than 1, the force increases. If you introduce a diamagnetic material, the force will decrease because mu R is less than 1. So for mu R greater than 1 implies F will be greater than F naught, and mu R less than 1 implies this is for para and ferro. This is for diamagnetic materials, then F will be less than F naught. These are the minor changes when you switch over from magnetism to electrostatics to magnetism. Next, in SI units, the proportionality constant in a medium is mu by 4 pi. Therefore, the force between the magnetic poles in medium, as shown there, will become mu by 4 pi into M1 M2 by R square. This is the force between them in medium. So it can be also written as mu R mu naught by 4 pi into m1 m2 by r square. So in case if m1 and m2 are already in vacuum, then that is the relative permeability is 1. Therefore, we get F naught is equal to, it is mu 0 by 4 pi into m1 m2 by r square. Then in electrostatics, you get another difference. F is less than F naught we got there. Whereas here, F can be greater than F naught or F can be less than F naught. That is the difference, another difference between electrostatics and magnetostatics. Then from this we define unit pole, just as unit charge there. Here we will define unit pole. What is the meaning of unit pole? If I have two identical magnetic poles situated in vacuum at a distance of 1 meter, then they attract or repel each other with a force of mu 0 by 4 pi. If you substitute the value of mu naught, then it will be 10 to the power of minus 7 newtons. Then if you substitute in this formula, we'll get m1 is equal to m2 is equal to 1 ampere meter. So the definition is a point magnetic pole, a point north pole, or a point magnetic pole which repels the similar pole situated in vacuum at a distance of 1 meter from it with a force of 10 to the power of minus 7 newtons is called as, yes, a unit magnetic pole of strength 1 ampere meter. I repeat the definition. A point magnetic pole, a point north pole, whatever it is, which repels a similar pole situated in vacuum at a distance of 1 meter from it with a force of 10 to the power of minus 7 newtons is called as a unit pole of strength 1 ampere meter. Okay?
Yes, sir.
Sir,
Have
can
you
you
copied
repeat
that?
the definition again, sir?
Yeah, the point north pole, the point magnetic pole, which repels an identical pole, which repels an identical pole situated in vacuum, situated in vacuum at a distance of 1 meter from it, at a distance of 1 meter from it with a force of 10 to the power of minus 7 newtons, with a force of 10 to the power of minus 7 newtons is called unit pole, is called a unit pole of strength 1 ampere meter. Okay?
Yes, sir.
Yes. See here, we wrote the units of epsilon as, yeah, q1 q2 by 4 pi fr square, that is coulomb square Newton inverse meter to the power of minus 2. that is I square t square by ml t to the power of minus 2 into L square. So this is unit, another unit. So we wrote the dimensional formula also as m to the power of minus 1, L to the power of minus 3, t to the power of 4, I square. In the similar manner, we can write the units as mu is equal to, yes, it is fr square by, see the switching over difference, m1 m2 into 4 pi.
Yes, sir.
Yes.
So the SI units will be Newton meter square by ampere meter into ampere meter, ampere square meter square. Therefore, this will be Newton ampere to the power of minus 2. Already we wrote as Henry meter inverse. This is another unit according to the Coulomb's inverse square law. Newton ampere to the power of minus 2. Dimensional formula, Newton, you know, ml t to the power of minus 2, I to the power of minus 2. Some books they are writing a to the power of minus 2 also. So this is about the units and the dimensional formula. And even we wrote the Coulomb's inverse square law in vector form as f bar is equal to f naught bar, whatever it is, 1 by 4 pi epsilon 0 into q1 q2 by modulus of r2 bar minus r1 bar whole cube into r2 bar minus r1 bar. In the similar manner, we can write the Coulomb's inverse square law in vector form for magnetism as mu 0 by 4 pi into m1 m2 by modulus of r2 bar minus r1 bar whole cube into r2 bar minus r1 bar. Even you can write it as f naught bar is equal to mu 0 by 4 pi into m1 m2 by r cube into r bar. So this is the Coulomb's inverse square law in vector form. And for problem's sake, we know f is varying inversely as r square. So f1 by f2 is equal to r2 by r1 whole square. Okay, completed?
Yes,
Sir, 1
sir.
minute.
Okay. Good. Finished?
Yes, sir.
Okay. So tomorrow we'll be doing the torque on the magnetic dipole and other related things. Magnetic field on axial and equatorial line of a dipole. All those things we'll do it in sequence in comparison to electrostatics. So it will be a kind of revision of electrostatics to you. Okay.
Yes, sir.
Yeah. Fine.